I see anybody's photo. You guys. Everyone. Please share, keep your videos on and keep the sessions more lively. Everyone. Yeah, let's start. Okay, I'm connecting from my this thing. All right. Shall we start?
Recording in progress.
All right. Okay, everyone. So let's get going. Do you have any questions before we start? No? No questions?
No, sir.
Abhijit, Bhavya, Disha, Madhumita, Prashant, Prateek, Satish.
No, sir.
Rupam, Sanish, Siddhartham, Sumasri. Okay, wonderful, wonderful. So, did anybody try to code it up yesterday? Whatever we discussed earlier? Nobody? Okay. I think a better thing would be for me to be is understand where are you guys in your journey. Abhijit, where are you in your journey? Till where you are confident?
Actually, I have done means last class I missed, but otherwise I am doing good. Yeah.
Okay. Okay. You are if given a chance like 1 hour, will you be able to code up the gradient descent, the basic one,
Yes. Yeah.
using Python?
Yes. Maybe I need to look something, but overall I can definitely.
Okay. Do one thing. Do one thing. I would tell you this. Okay. Look into your calendar. Okay. Look in your calendar and block 1 hour time for this. Okay. Just think of it as it's like a interview going on with somebody. Okay.
Mhm.
And then let's say next week sometime, just block your calendar for 1 hour and code it up as if you are giving the interview. What do you say?
Okay. Yeah.
Yeah. Just take out some 1 hour big slot of time and put your watch, a clock, and then code it up. Okay. And during this, whatever you need to look, you do that. Think of it as somebody is taking the interview.
Okay.
Okay. I think that's a good idea. Or what you guys can do is you can be each other's interviewer, like two people at a time, then coordinate, block each other's calendar, be at that time, and do that, code it up. Because what I understand is that a big trouble with learning, given all of us are kind of mature, is to basically take out the time and sit down and get it done. Okay, if there is an external commitment, you will do it. Otherwise, it would never happen. Okay, like going to the gym. Okay, so if you can get somebody as a buddy, and then you basically each one observing and giving the score to each other, that is better. Okay, so you can buddy up with the team here, and then yeah, aim for right. Just block 1 hour for your interview and 1 hour for some other person's interview. So in one, you are the interviewer, other they are the interviewer. Okay, makes sense.
Yeah.
All right, Bhavya, where are you with in your journey?
Good morning, sir.
Yeah,
Sir,
where are
actually,
you
I have
up
been
to?
not attending many classes. I was traveling from last few days,
Okay,
so I need to catch up with the classes.
okay. Okay. But till what topic you are confident?
Uh, Sir, recently, yesterday only, I was doing the coding for Python loops and all that.
Very good. Very
Yeah.
good. Okay. 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 And yeah, I would say that once you go through, I mean, you don't have to go linear, just jump into last couple of lectures and then go
Okay.
from there. Okay.
Okay.
Just start right away from the day. I think four or last 6 classes only. Okay, I think that's where we started coding up the gradient descent. Okay,
Okay.
yeah, just jump to that. Okay, code up the gradient descent, and that's it. Okay.
Okay.
The other things you can backfit, as in whenever you get stuck, start looking up, and then you can do. Okay.
Okay, sir.
All right. All right. So I would like I'll do this way. Okay. So just on the WhatsApp group, everybody can post where they are in their journey, up to what topic they are confident. Okay. And then you can buddy up with each other. Okay. You can buddy up with each other, like two people at a time. And then you guys can be like one, right? Help each other. Okay. It's more like a co-study than being each other's mentor. It's more like a co-study, like we were studying together. In case we have a doubt, we basically would ask somebody from the group, or we'll try to resolve something. It's more like making sure that you have an external commitment to study. Okay, it's only for that. Okay, having an external commitment for studying is something that's important for all of us. Okay, so just like post where are you in the journey and in which time zone you are, and right, and then basically you can buddy up. I would strongly recommend that you buddy up, like two persons. You create a group of two people, and then you can work together. Okay, and yeah, and I think that should help all of us. Okay. It's more like a commitment time. When you give a time to the other person, you show up at that time. Okay. And you basically make time forcefully. Otherwise, what happens is if you don't have a time blocked for somebody external, you do not sit down because you have like 100 things waiting here and there. Go get some dhania patta, go get some like get some milk, or do this, do that. You have like 100 things pending, and because of which you end up not working on yourself. Okay, so it's important to have that commitment time. All right, I think yeah, this is a good exercise. I would strongly suggest that you guys should just post where are you in your journey, and then buddy up. Make just 2 people, not more than 2 people. Okay, just 2 people. Okay, and yeah, and also share your time zone so that you can work with somebody. Okay. All right. So I think that's a good exercise. Does this sound like a good idea, everyone?
Yeah.
Yeah.
I don't see anybody's videos. Why? Okay. Yeah, I can see Abhijit. I can see Nikita. Thank you. Okay. Nikita, you look very young, like you are in 3rd year or so. Yeah.
Yeah, I almost my graduation.
Okay.
Sandeep, I turned on my video, but it's my kid's birthday. So his friends are coming here soon in next 5-10 minutes.
Okay.
I'll then shut down and mute myself off to avoid any disruption.
Okay. Okay. All right. All right. Perfect. Perfect. Wonderful. Wonderful. Okay. So yes, it's actually good to get. I'm so happy that most of my learners in the past are doing well. I keep getting messages from people from my my previous batches, and yeah, for an education institution, it takes 10, not 10, like 20 years to become somebody. And yeah, I think as the time is passing, most of my ex-learners are becoming somebody who's who. And that's what is going to be. Like for IITs to become IIT took like 40 years or so. Okay. So yeah, this week has been pretty good. Now let's move on. I shifted to a new
So
place.
I had texted you regarding the fellowship that you mentioned last week.
Okay, okay, okay. Let me reply to you. Okay, and yeah. So fellowship, yeah. I would love to have you guys in my fellowship program. I'll message you the calendar link, and then let's have a one-on-one discussion. And yeah, so I'll chalk out some projects so that one person. I have given one project to Shubodh and one project to my previous batch learner Amit. One project to Aman from the group, and I'm planning to give out more projects now. And yeah, by the time you guys finish, you finish your graduation and other things, a lot more things are waiting. Okay, and yeah, so now the thing is that a lot of work is coming my way. People are approaching all the time, so I would like to have more people connected with me, and the fellowship is a good strategy in the sense that as I work with you, I know your strengths and weaknesses where you can be good at, and then basically I just connect you and put you in touch with one of the people who is approaching me for the work. So yeah. And yeah, specifically this particular batch, I'm pretty happy that everybody got on to coding. And I'm very happy that even those who are very experienced, they got onto coding. And I can bet, and I can guarantee that part that you'll do pretty well. And you'll do pretty well in general. Okay, so you will naturally see a lot of opportunities coming your way. Specifically, like I am myself very confident that right, if I give the project, you'll be able to do it. Okay, so that way. So yeah, well, so take out your time as much as possible to start coding, and yeah, and reach out to me if you are up for good fellowship, and then I'll we'll connect. The other thing is that yeah, the good part is that if let's say somebody does a good work with me for like 2 months, I can write a recommendation for you if you're planning your master's or something. Okay, provided you do good job. Okay, and I would I also would talk to Professor Raksha, give my recommendation to her that there's a candidate who has done this, and she or he is from my batch or our batch, because this class is of Professor Raksha and mine. So yeah, so she can also probably give the recommendation letter. Okay, based on my yeah. Or maybe she'll have like one-on-one interviews or something for giving the recommendation. So that way, those are the advantages of fellowship. And yeah. So with that, I think let's get started. So I think more, I mean, this course is not like a course per se. It's more like a proper, like a career change kind of a thing, like something that like MS programs or MBA programs are not able to achieve, or these courses are able to achieve in 1 year. And that's actually, I'm pretty happy about. Okay. All right, let me just close all my windows. Before I start, any other questions?
Not really, but one feedback, this is a good, learning program for individuals who are having good experience. Like people like me are in IT like 20 years almost. It's a change of thinking, that this brings in. So
Thank you.
that's the thing that I like about this. It helps you to think, basically in the first principle, following first principles, and that's the thing that I like about this.
Thank you. Thank you. And I can guarantee that this class is going to be very hard to manage for anybody else. Okay, most of my classes are very difficult to manage for any other professors. Okay.
Can't comment on that, though.
Yeah, I've seen it in past. It takes a lot of courage to manage the class, because most of my learners become very first principle thinkers, and they question like normal things, and they don't take the right. They actually, there has been issue with some of the classes, and I'm happy about it. Okay.
Yeah.
I'm very happy about it, that that just shows that that if you are teaching a Westerner. So there have been like there was a Russian guy who was a mathematician who was attending my classes, and he had very hard questions for me all the time. Even one of the Firefox, the Mozilla Firefox principal engineer of that one was attending one of my classes. So she had very hard questions, and so most of the Westerners are as in they have they don't shy away from asking nonsensical questions. Okay. And they're very fearless when asking questions, and just too much fearless, I would say. Okay. Right.
Yeah.
But with from people from Asia and India, we kind of are very too respectful to the teachers, so we kind of do not ask questions, much questions. And what I would say that like what my class does is like at least push people from being shied away from asking questions to somewhere they can ask more and more questions, and just give everyone this trust that your questions are welcome. Okay. And yeah, that is something. I think whenever you also, when you are teaching a class or something tomorrow, make sure that you follow that tradition, that every question should be answered and respected. Okay.
Yeah.
That is, yeah, that is an ask that I have.
Yeah.
All right, good. Yes, Veena, did you code the using NumPy?
Oh, yeah.
Anybody coded with NumPy? The gradient descent?
No.
Oh, okay. Okay. All
So,
right.
I just found one issue. The gradient isn't that first initial thing, right? Without NumPy. Even that, it is giving good result. If I'm giving the training data, like we took, I think, 10 points. But if I'm increasing that training data to like say 50 or more than that, then that result is not coming for me.
Okay, showing.
Yeah.
You know, this is real. What we are doing is real. Okay. So when people were doing gradient descent long back in 80s, and they were experimenting with various kinds of data sets, they actually declared that gradient descent doesn't work. Okay. But then came the activation function, right, in the multi-level perceptron, and that changed everything. And that was like a magical thing. So yes, I think, yes.
Yeah, I will just run every cells. Run all. Now I'm getting good results actually. I'll just show you. This is the result. It is coming down to the value that I have given 14. I'll just show you what I have given. 15.
Awesome.
I think 15x plus 4 is the value that I've given.
Okay.
It's giving me good values. But if I'm making it to 50.
Okay.
Yeah.
And so that's your data. Okay, go ahead. Let's see. How does it look? Let's plot it and see. Go slowly, one step at a time. Go slowly.
Okay. This is...
So you have increased. Okay, perfect. Let's move ahead. Yeah. Just do one cell at a time. Just do.
Okay.
This much patience you can have. Okay. Yeah, go ahead. Yes, amazing. So 50 data points, little bit variant. Okay. And then we have the squared error. Okay.
This is derivative.
And yeah, this is derivative. Okay. And okay. This is differentiation. And then, okay, you have chosen MNC randomly. And then you are doing this. Okay. Let's take a look. Now it's going crazy.
Now it is going crazy.
Crazy. Go up. Let's see where are we making a mistake from the beginning. So current loss was this. So it is increasing, right? Can you drop the decrease the learning rate? Let's just put 1 more 0. Let's see what happens. Okay.
Have to come again, right?
Oh, okay. Okay. Can you go down? Go down. There is a mistake there, right? There is a mistake. I'll tell you what's happening. Come down. Come down. The follow-up. Yeah, this is the. So can you take out the weights, and put it outside? Every time it's going random. Okay. Yeah. Yes. So because we are going to tweak. No. No, I think previously it was correct. Because you are updating the MNC.
Yeah.
No, good. Yeah. Previously it was correct. Yes. Okay. Now let's just test it out. Can you run it? Where are we wrong?
I just changed the eta value.
Yeah. No, just run that loop again.
Okay.
Initialize MNC. Yeah. Initialize MNC, and then and do that. Yes. Okay. So is it going down or going up? Okay. Okay. And 1C1. Okay. Let's reduce the eta a little further. Let's see what happens. Is it because of eta or some other problem? Anybody? Any ideas onto this? Okay. All right. This is squared laws.
Now I'm getting, I think. Yeah, now I'm getting.
Okay. Basically, the learning rate is the problem in this case, right? Yeah. Okay. Yeah. Is it there? I think this has saturated very quickly. How many epoch did it take to saturate? Go up. This much error would be there because of randomization. Five iterations in done. Okay. So what did we learn from this? If it's exploding, you should just reduce the eta. Okay. All right. Wonderful. Wonderful. Good. Very happy that, yeah, we debugged it now. Okay. Rather than later. And I think the most important algorithm to learn is the gradient descent. Okay. The reason I'm emphasizing it is that probably Nobel laureate, the people who got the Turing Award, if they are going to teach neural network, probably they will only focus on the gradient descent mostly. Okay. Because if you see, unsupervised learning today is based on gradient descent. Supervised also is based on gradient descent. We learn how to structure the problem statement so that you can use gradient descent for reinforcement learning, computer vision, for let's say LSTM, for all the things that you're going to learn in machine learning is going to be gradient descent based. Okay. Essentially, tweak the knobs such that the loss is minimized. That's all. Okay, let's say tomorrow we are going to work on, say, ChatGPT, right? What does the training mean? Tweak all the weights such that it gives one of the suggestions as compared, like out of the dictionary, it gives one of the words. That's all, or one letter at a time. That's all. Okay, so the classification essentially. So we'll learn how do you translate the regression to classification, and from classification we'll go to this one, and then we'll see that how can we convert this into multi-layer, and then we'll right. So that become very easy for you. The other algorithm that you're going to learn as part of the machine learning would be like SVM decision tree, and yeah, those are the main things that you'll study, and then little variants of the decision tree called random forest and XGBoost, the gradient descent, the gradient, extreme gradient boosted trees. Those are essentially decision trees variant. Okay. All right. Perfect. Anybody else is stuck? Okay. This is a very good exercise. Thank you, Veena. And anybody else is stuck? No? Okay. You should just give it a shot. And yeah, I want everybody to help me out today. Okay. I was hoping that some of you would work upon the place where we left last time. We left here, this one, right? So we're learning NumPy by the way of upgrading our gradient descent to
Sharing.
Oh.
I named it right.
Oh, sorry. Okay. All right. Yeah, pay attention, everyone. You have to help me out. This is something that I would require your help. Okay. So I'm going to work through this problem in the class, and that's how I'm going to do. Okay. And don't judge me because I'm also pretty poor at NumPy functions. So though I'm able to solve most of the problems, but that's how it is. Okay. Long back when I was in college, one of the Linux authors, like big guy, came to our campus, and we requested him to help us in some Linux configuration in the college. So he was like a kernel developer, big guy, and you were thinking that he'll just type one command and he'll just get it done. But when I was sitting on the next to him and observing, he was also doing the way I'm going to do the in class today, seeing through the documentation, read through the manual, and try this, try that. So yeah, so even the most expert people, they do this all the time. Okay, right. I was the other day I was like talking to Aurelie and Jeron when one of the I'm a fanboy of that guy, and the guy who has written that book Hands On with Machine Learning. So when I met him, so he was explaining that he always struggles with Pandas API and specifically Pandas and Matplotlib API. And as he was just sitting next to me because we were speaking the same conference, and all the time when he was coding up, he was just looking up the documentation of Matplot and updating his next version of book. The book that you see right now, he was editing that book that time. Okay, so all the notebooks and everything, he was just each function he was just looking at manual, fixing it. Okay, so this is how everybody does. Okay, this is how everybody does. If somebody is able to just type all the commands in one single shot, know that he only knows that part. Okay, know that that person only knows that part because it's not humanly possible to memorize any function. Okay, the only way to get things done is know the logic, think about the logic, and then utilize the manuals and look up. Okay, so yes, so this is what we are going to do. This is a comment. Okay, now I'm saying this connector, right? NumPy, imported NumPy, these are, M is going to be number of experiences, N is going to be number of columns. It's a standard terminology, so we should live with it. M means instances, or we call it samples, data points, experiences. Okay, these are few of the terminology that we use for M. And N is features, or what else we call them. Okay, right? These are the columns usually, and these are the rows. Okay, what else we call them? Features. Others are instances. M is instance, N is features. What is the other name for features? Attributes, dimensions,
Tables.
characteristic. Table, no, so N, I'm talking about N.
Labels.
Labels. A label is the one feature, the output we are expecting. Okay. Usually one of the dimensions, one of the columns is your expected output. Sometimes more than one. So based on the features, we translate features into an output. Okay. What else? Characteristics, dimensions, attributes, columns, features, and okay. All right. Okay. So yeah, we just want to show you that if you are going to, okay, this was how the random int work. Okay, this is how the random int works. Okay, so we can happily ignore that. Okay, and we also talked about the random seed. Okay, so or let me just leave it here. Okay, yeah, let me just leave it here. Okay, this part I just want to show you that in case we are going to this is to record the values of random numbers. Okay, now what we are going to do is we are going to generate X. Cool. So X is going to be how many values? M rows and N columns. Correct? So M rows experience and N columns. Okay, so this is my data. These are the attributes. These are the attributes. Right now, we have taken an example of 4 features. So it had generated 4 column, 4 columns and 100 rows. Not 100 rows, 10 rows. Okay. So, and now, this is my data set. Now, what I'm going to do is I'm going to generate my Y. Okay. All right. So shall I make a new notebook? What do you say? I'll just make a new notebook. I'll just call it September 6. Okay. And we'll copy whatever we need as is. Cool. And there we go. Perfect. What else? This is not required. This is needed. Okay. So this is the exercise is going to be gradient descent, coding gradient descent using NumPy. And we have been experimenting with all of these parts. Okay. Let's take a look at this. Okay. Now we said here, okay, so X is my, okay.
Sandeep,
Yes.
if you don't mind, I don't know whether I missed that class, but if you can also help us to, explain the objective of NumPy, when we should use NumPy, when we should not use NumPy, and what all the feature of NumPy, I think that will help us to build the foundation also.
Correct. So see why we are using NumPy. So in the earlier classes, when we were generating our data, we were writing loops that for 10 times 10 rows of data, we will generate these numbers and so on. Correct? Here, NumPy will eliminate the need of the loops. Okay? So we will essentially, rather than iterating, okay? So 2 things that NumPy provides us. Okay? Number one, an efficient array. Okay. Number 2, a powerful set of functions that eliminate the need of for loops. Okay. And yes, I'm not going to go with the bookish definition. I'm going to focus a lot more on the practical applications of it. So whatever we coded as part of our previous exercise, we basically are doing the same thing using the NumPy. Earlier, we wrote the for loop for generating data. Now we are just generating using the NumPy function. We can generate random m cross n matrix, meaning m rows and n columns. So this is generating kind of an Excel sheet that has m rows and n columns, so many random numbers. Okay. Why are we generating? We basically want to generate our data set so that we can build our machine learning model on it. It has m rows and n columns. You can see that. So NumPy provides these powerful functions, which helps us eliminate that need of writing for loops. Okay. Now, if we want to generate Y from it, earlier what we did, we went through row by row, column by column, multiply weights, and then generate an outcome. Okay. So now what we are doing is we are using NumPy to do that multiplication in a single shot. Okay. So this basically becomes very efficient when you are using GPUs or when you're using powerful CPUs, which can distribute things. So the way it works is right now, let's say here we are using, let's say this function that you see here, it will take X and W, multiply W with X, and will give us the result. Okay. Okay. So let's see how it goes. Okay, we tested this out last time. So let's say we have this X and we have, where is our Y? We used all of this. Yeah, okay. Let's take a look at this example. So if you have W that contains 3 rows and capital X that contains 2 by 2 matrix, and you want to multiply W on X and it generates our Y. Okay, let's take a look. So it has generated 80 by this. Okay, so what we are saying here is, this. Where is my pencil? Yeah. Okay. So what we are trying to say here is pretty simple thing. Okay. Right. So what does the dot here means? It's calling the dot, right? Before that, it's adding 1 to it. So we have 1, 2, 2, 3. This is our X. And we are multiplying with W, which is 10, 20, 30. Correct? What we want to do? We want to compute Y, which is, let's say, W1, X1, W2, X2 plus W. Something like this, correct? So why are we doing this? We want to generate the data for our experimentation. So we generated X, okay? We generated W's, and now we want to generate Y, okay?
That Y, that W value, that 10, 20, 30, that will be one row, right? It will not be a column.
Yes, yes. Guess, okay. I'll come to that, okay? Right? So what we are doing is here, okay? What we want to do is, we have generated, let's say, we secretly know what is the W, okay? What's the exercise? Exercise is, we are given X, okay? We are given X and Y. Find that function that takes X and generates Y. We have to find this function that takes the input and gives the output. Okay. Now we are saying this function could be linear. Okay. So let's try to find that linear function. What does it mean? This function is W0, W1, X1, W2, X2. We are going to do this. Okay. Right. We're going to do the linear thing. And for that, we need to generate the data. So right now we are just generating data, and we have generated X, we have generated W, and we are going to generate the Y. Okay. Is everybody okay so far? Ranbir, was I able to answer your question that you asked?
Yeah. Yes, Sandeep.
Okay. Okay. All right. Now,
Sandeep, can you help me? Why we are generating Y?
we are basically generating our data, honestly. Okay. Right. We are saying that, okay, we have a secret equation, and that secret equation is, again, we have, used the random number generation to do the secret equation. And then we're basically generating our data, X and Y. Okay. And then we will hide W somewhere, and we will want our gradient descent to find that W. So gradient descent's duty is to find the W, okay, given X and Y. Okay. So right now we are just creating a problem. We are just creating the problem data set. Okay.
Got it.
So, okay. So what we are doing is, in order to, what we want to do is, Y1 is equal to 10 plus 20 times 1 plus 30 times 2 plus something like random number. Okay, y2 equals to 10 plus 20 times 2 plus 30 times 3 and plus some random number. Okay, so this is the example that I want to show you. Okay, so we are adding, we want to do this in a single shot rather than we looping through this data. We already have generated X, so we could have just written a for loop. But a better thing is just do the dot product. Okay, and if you do add 1 to this one, so what happens? This row multiplied with this, which is 10 plus 20 plus, sorry, yeah. So it's the other way. It's the other way. Sorry, it's the other way. The other way is the other way. What we are trying to generate, we are adding 1 in the end. Okay, we are adding 1 in the end. So we are saying 10 times 1, 20 times 2 plus 30 and 3 times 20 and 2 times 10. Okay, is everybody okay? This is the definition of dot product. So first you take the row, multiply with the column, then again the row, multiply with the column. Okay, let's take a look. This is 40 plus 30, 70 plus 10. So 80. This is 20, 20 plus 60. 80, 80 plus 30, 110. Is everybody okay with the dot product and this particular part? So we have, let's say 10, 20, 30, the weights, and we have the value of X. What we are generating is the value of Y. And how, one way, we could have just written our loop, for loop, but a trick, a smarter way is using the dot product. Remember, the dot product is a part of, the standard linear algebra things. Dot product's definition is exactly this. Take the row, multiply with the column, take the row, multiply with the column. Got it?
So it is same
matrix
as
dot product.
so it is same as the matrix multiplication, right?
Yes, Nikita. So if we have, let's say this has 100 rows, and this has to have 100, and these are 30 columns. It will generate basically same amount of results. Got it? So this model, what it does is it adds empty column, 1, so that we can just add 30 to everything and so on. If we don't add this, what happens is it will do 10 times 1 and 20 times 2. It won't add 30. It will throw an error. Correct? So what we did was we basically made it like X0 everywhere, just to make it like seamless. Everybody okay so far? So we have written a function called model, which takes W and X and it gives Y. Okay. Instead of using loop, we are using a function called dot product, which does this in a single shot. Yeah. The silence is killing me. Go ahead. Yeah. Everybody okay so far? We are just generating data, by the way. We have generated X. Now is the time we generate Y.
These are the Sandeep. Sorry, I had missed last 1 or 2 classes. Actually, 2. So these are the standard functions of the available in the NumPy library, right?
Yes.
The edge stack and all this.
Yes.
And the dot product. So this dot product is a matrix product we are talking about.
Correct.
Okay.
Correct. So we are using multiple functionalities of NumPy, right? So first we are taking an array 10, 20, 30. we are putting it in W, right? Then we are here defining capital X, which is a 2 by 2 array, right? This is 2 by 2 array, and this is a 1 by 3, basically a vector. Okay, this is essentially a vector. No need to say 1 by 3. We can just say 3. We call it like this. Okay. Now what we are doing, we defined a function called model, which takes X and W. And then what it does first, it finds how many rows are there in X. How do you find that? We can say X dot shape, which will return 2, 2. We are saying M equals to 2. So M is equal to 2, right? Now we are generating ones. How many ones should we generate? As many instances are there. So we had 1, 2, 2, 3. These are our instances, right? And we are saying generate 1, 2, which is basically this, right? This kind of, so this is essentially once is going to be look like this. Okay. So it has got 2 rows and 1 value in each. Okay. Make sense to you? No.
Yes.
And then we are saying, take this and take this and stack it here. Okay. So stack it here means just put these things into the same place. So it'll basically, okay, append this one and this one into this. Okay. So 1, 2 and 2, 3 will become 1, 2, 1, 2, 3, 1. Cool. And then we are saying dot product. Okay. Dot product, what it does is, so H stack concatenates the columns and in some direction, and then dot product basically does the multiplication of matrix multiplication. Okay, what is matrix multiplication? We take the row, multiply with the column. 1, 10, 2, 20, 1, 30. Then we take another row, and then we say 2, 10, 3, 20, 1, 30. And this is where we get 80 and 110. Cool. So our function is working. So now we are ready to use this function for everything else. Cool. So this function takes X and W, gives us Y. Okay. Right now we don't know W. Right now we know W secretly because we are generating data, but we will park it W aside and we'll only use X and Y. And then what we'll do is we'll guess the value of W, ask model the value of Y, and then compare the predicted value with the actual value, and then try to tweak the W's until we reach to a point where Y predicted and actual is same. Everybody okay with that? So we have this function called model, which takes X and W. So, okay. Okay. Model takes capital X and it has W with it. It gives us Y. Okay. So X is essentially, whatever data you have, you give it like input data, it'll give you the output. Okay. So what we're going to do in future, just make a guess for W initially, and then compute the predicted value of Y, compare the predicted value with the actual, and then we'll keep on tweaking W's until our predicted values are very close to actual. Okay. So first, what we do is we usually the model is also called H. Okay, H means hypothesis. Okay, so we always say, all right, given X and Y, figure out the model. And once you have figured out this model, we'll say we'll do the prediction using this model. Okay. So what does this mean? Given an experience of past, along with the labels, we are learning the hypothesis. We are learning from the past. Okay. Once we have learned, we use this to predict the future. Okay. So first we learn. So this is the phase number 1, learning phase. This is the prediction phase or inference phase. Okay, everyone?
Sandeep, if you don't mind, maybe
Mhm.
question seems stupid, but can you repeat why we are using x dot shape 0 and you define another variable 1 and then np dot 1 m and 1 and then np dot at stack. So can you just explain one more time if you don't mind?
Yeah. Okay. So this is clear to you?
Yeah.
Okay. Let me start from here. So this is clear.
Yeah, this is clear. W
This
and
is
X.
also clear. This is also
Yeah.
clear. Perfect.
Yeah.
This one is clear. X dot shape gives us two values, 2, 2, because it has 2 rows and 2 columns. Correct?
Okay.
Right? X has 2 rows and 2 columns. Correct? So let's go up here. We are saying this. Yeah. We are saying this. Here we are saying, give me M. How do we extract M? We'll say shape and give the 0th value. Okay. What will be the 0th? This is 0. This is 1. So it will give 2. Correct? Okay. So M is 2. Right?
So shape is an inbuilt function in NumPy?
NumPy. Correct.
Okay.
Shape is an inbuilt function of NumPy. Okay. The array is an inbuilt function of NumPy. What it does is it converts any array, any Python array into NumPy array. Okay. Similarly, this shape, because X is a NumPy array, on the NumPy array, there is a function called shape, which provides the shape of X, and we pick the 0th value, that is number of rows. Okay.
Yeah.
Now, when we say np.once is basically a NumPy's inbuilt function. Okay. When you are, please notice this here, when you are asking for a variables information, or you're calling some data on this, right? You can simply call the function on that particular array. So either you can use np dot this kind of functions or this. There are 2 sets of functions. One set of functions are in np module. Other sets of functions are in the array object. Okay. So this is an array object X. NP is a NumPy module. Okay. So here we use the X dot shape. It gave the shape of X. Here we are saying NP dot once. This is a function which generates the array of this shape containing ones. Okay. So if you want to generate only ones, let's say NP ones. Okay. And you want to say, give me 5, 6. So it will generate 5 rows and 6 columns of n ones. Okay. If you say np.zeros, okay, it will generate 5, 6 size array filled with zeros. Okay.
Got it.
So here we generated m number of same size as these many number of ones. Okay. Why? Because we want to insert one more value called 1 into each of them. Okay. And how do we insert that? Using the add stack. NP provides, NumPy provides add stack function to insert basically one element into an existing array. Okay.
Thanks, Sandeep. I appreciate it.
Okay. So if you see here, all right, if you, let's say, take this, okay, and okay, so the X right now looks like this, okay, and X1 looks like this. So 1, 2 became 1, 2, 1, 1, 2, 3, 1. Okay. And if you, let's say, take this, okay, and now insert one more into this, okay. You can see it would okay. So you can see now we added one more one to it. Then we can keep on adding one more one to it. Got it? You see that? It's increasing. Cool. So we are just appending ones to that thing. Now the dot product is okay with you, Ranbir?
Yes, sir. Dot is fine.
Okay, perfect. Perfect. Now I'm going to delete this, delete this, delete this, delete this. Perfect. So model is doing a good job. Okay. All right. Now we go on to this method called generate data. Okay. And in this, what we are doing is given M and N, we are generating the data. Okay. So we are not actually using any of this function right now. So we are setting the seed 10 so that whatever weights it is generating secretly, we can use them. Okay. So what we are doing is first we are here you can see we are generating the weights, then generating capital X. Using capital X and C, we are generating Y. If we generated Y also pure randomly, there will not be any correlation between capital X and Y, and therefore our system will not be able to figure out a correlation. Right now, there is a hidden correlation between these, and that correlation is these weights, okay, or coefficients. Ideally, we should just call it, W, because that's a better terminology. Okay, so we are using the model to multiply X and W plus some random values and adding it to Y. Okay, that's all. Make sense? Yeah. And also notice that here, how many values will this model produce? That is my question to you. Here it produced 2 values. If this has 3 columns, okay? If this has 3 columns, okay, we will need one more weight, right? We'll need one more weight because if you have 3 columns, you'll need 4 weights, correct? And here it would again generate same number of records. One, like, if it has like 100 experiences, it will generate 100 Y values, correct? One value per row, okay? This will generate the values equal to, right? So W will be, okay? Is everybody okay here? Now, so yeah, so this will generate how many values? As many rows as X have, which is M number of records. It will generate an array of M size. Now we are adding M number of random numbers, okay, by multiplying 2 to each of the random numbers and subtracting by M random numbers like this, okay. Perfect.
So Sandeep, if you don't mind, then what is this? What we can call it in a mathematical way, the way where you put model X by and plus adding 2 times and subtracting 2 times. Is there any mathematical formula for matrix or vector or anywhere which we are using here?
This one.
Yeah, this one.
This one is essentially going to generate random value between -1 and 1. sorry, random
One.
number generates 0 and 1. So -1 and 1. Correct? So this one will generate a random value between 0 and 1. Okay?
Okay.
So this one will generate random value between 0 and 1 minus some random value between 0 and 1. So this will basically, in worst case scenario, if this turns out to be 0, this turns out to be 1, the smallest value will be -1. And the highest value is going to be, if this turns out to be 0 and this turns out to be 1, 1. So this will essentially, what we have done is, right, we have simulated a function to do the random number for us. Okay, so random, how can I, is there a way to do, let's say 10,
Maybe
10.
run-based question is like, why do we need to have that? It's just for randomness when we that we are doing that. Exactly, we don't want the exact why. We just create a randomness. I don't know whether that is the
Yeah. Basically, see, if it was all perfect, right? Let's say we are generating the data like very perfectly. Okay, so all the data points will be just in a straight line very nicely. Then we don't need that many data points to figure out that equation. We can just pick 2 data points and we can figure out that equation. What we want is, we don't want that perfect world. In real world, what happens is the data that you'll get will have a little noise in it. So it would look like this. Okay, in real world, the data will not be a perfect straight line. It'll look like this. So we have to figure out a line fitting through this. That's why this amount of randomness we are kind of introducing in our data. Is that your question?
Yeah.
Okay, good, great. Moving ahead. Okay, so we wrote a function called generate data, and here we generated the data. Okay, and it's also is printing the coefficients. Okay, we can anytime we can generate these coefficients by using this technique. Okay, we could just say how many coefficients are there. Okay, so right, you can see that at any time we can generate these coefficients. How are we generating? By fixing the random seed. Okay, just to ensure that we don't miss out on this, because in the end, when we figure out these values, we would like to come back and check whether we have found out the similar coefficients or not. Okay, we'll just see that in the end. Okay, all right, then where were we? We kept on moving. Okay, yes, this is something that we were doing here. Okay, all right, we were doing this. Okay, now what we got to do is, let's say we have X and Y and weight. Okay, so what we want to do is, given this data, the capital X and Y and some random weights, we want to compute the rate of change of W's, rate of change of loss with respect to W. Okay, why are we doing this? Why are we doing this? In a real life problem, we will be given X and Y, and we have to find those W's that translate X into Y, correct? So we want to find out those values where Y predicted is very close by, this is very close by to actual Y. This is very close by to the actual Y. So we want to come up with those W's that give me the output near to the actual. Okay, that's what I want to do. Make sense to everyone? Right? For that, what I want to do is, I will slightly increase the W and observe, is my loss going near or far? Okay, is my loss going near and far or far? Okay, so and also notice one very important idea that in this here, the where was that model? Yes, in model, okay. Just see. Okay, so this is my model. Okay, now if we have multiple rows of W, okay, let's do this experiment properly. This will make it very clear. Okay, so one set of W's are these, and let's say we have one more set of W's. Okay, one more set of W's. This, okay, let's say 11. Okay, so it says that we basically these 2, 4, and this is not aligned. Okay, let's try to understand what happens. So what we need to do is we need to do the W and W transpose here. Okay, we'll do W transpose. Okay, I'll explain to you now. You see, so what we did was we want to do, if let's say somebody gives us multiple sets of W's, we should be able to compute the values of predicted Y. Okay, we should be able to compute the value of predicted Y against the actual Y. We should be able to compute the predicted Y. So we are given X 1, 2, 5, 2, 3, 6, and we have added 1 to both of them, right? And then we are multiplying here 10, 20, 30, 40, 11, 20, 30, 40. Okay, so what we did was, this was basically, it has 2 rows and 4 columns. So we did a transpose. Transpose means that rows became column and column became rows. So 10, 20, 30, 40, 11, 20, 30, 40. So the moment we said W dot T, it basically flipped W. Now we can happily multiply. This row gets multiplied with all the weights. This row gets multiplied with all the weights. Make sense, everyone?
Yes, sir.
Perfect. So we can simply use the same philosophy here. So we will write a fresh one. Okay. All right. So we'll say whatever our W's, let them be. We are going to do is we are going to predict the value. Y predicted is equal to model X, Y, X and W, right? This is what our model is predicting. Okay. And okay, so this is the Y, this is the predicted value of Y. This is the predicted value of Y. Now what we want to do is we want to, okay, right? We want to compute loss. Okay, how do you compute loss? We are given X, Y, and W. Okay, how do you compute loss? You first produce the Y predicted. How do you do? Model X comma W. It gave us Y predicted, and then we subtracted Y from Y predicted. Okay, and then we did the square. Okay, and then we did the, okay, like this. Make sense to you? No? Okay, let's see. So this is our loss. Okay, and we are returning loss. Okay, now here the W could be multiple columns, right? Could be multiple columns. Okay, so how many columns will it generate when you let's say here there are multiple values of let's say here there are let's say I'm just adding 2 more. Okay, I'm just adding 2 more just to make sure that we are okay like this. All right, so once I modified 10 to this, then I'm modifying 20, then I'm modifying 30. Okay, and I'm going to delete this. Okay. Okay, so what I did was, let's say I have generated, okay. Okay, so I am passing 5 W's, okay? I'm passing 5 W's and these many values. So the output will be 2 rows by 5. So how many ever W's are there, that many columns are going to be here, okay? And it will have same number of rows as X. So I hope you got the idea, right? So how many ever weights you are passing, those many columns are going to be in X, and the number of rows are going to be equal to the number of rows in X. Okay, so let me just go back here. So I said model, right? Right. So here what will be the shape of Y predicted? It will have M. M is the number of rows and rows of W. How many ever W's are there, that many rows it will have. Okay, that many rows, that many columns it will have. Okay, so if you are passing 20 W instances, it will have 20 values of Y. Okay, now what we are doing is we are asking model to produce those value of those predicted values, and we are subtracting this. How many values will be in Y? What is the shape of Y? Okay, let's see, right? Shape of Y is what? Shape of Y is equal to M times 1, right? M are experience and 1 is the value. Okay, so and what's the shape of W? The shape of Y predicted is this much. So you can think of it this way, that if let's say Y was this, okay, and Y1 is equal to how many? Sort of 1. Okay. Okay. Something like this. So Y1, the Y predicted would look like this. Okay. It will have same number of rows, rows as this one has. Okay. And but it will have different values of basically the number of columns are equal to how many weights we are passing. So if we say Y predicted minus Y, okay, so okay, I'll just convert it into NumPy array. Please pay attention here. This is going to be important and help me out. Okay, don't only pay attention, please help me out, because I wouldn't really know when I lost track. Okay, so what actually happened here, right? We are subtracting from this 2D array a 1D array. So this element is subtracted from this and this. Okay. Sorry. What are we trying to do?
It is subtracting the other way. Y predicted minus y, right? 1.1 minus 1 and 1.2 minus 2.
That means it's wrong, right? That means it's wrong. Okay. We need to change the y a little bit. Okay. How do you change? We'll say reshape, and we'll say make it into something like this. Make it something like this. Okay. All right. Let's just change its shape. Reshape. We'll say whatever are columns, I don't care. Just make it this. Okay. Let's see. Yes, now it makes sense, correct? So we want that 1 should be subtracted from these 2, 2 should be subtracted from these 2. Okay? Are you guys okay with this? No?
I didn't get that. Why are we subtracting this with the y predict?
Okay. See, y predicted has got, when we are, let's say, generating predicted y using multiple sets of weight. First set of weight generated this and this. Second set of weight generated this and this. Correct? Okay. Yeah. Right. So essentially, first set of value of y is this, and this 1.1 and 2.9. We want it to be subtracted, like 1 should be subtracted from this, 2 should be subtracted from this. Okay, 1 should be subtracted like this. Okay, think of it this way. So our predicted y is 1.1, 1.2, and then 1.2 and 2.1. Okay, for one set of weights, when we put one set of weight, okay, for first instance, whatever was our first instance, we got this as the predicted value. For second instance, for second weights, so for first, because what we're going to do, we have the x, right? The experience y, the historical experience x. Okay, we made a guess for w1, some random guess for w1. Like, okay, these are my first set of guesses. That gave us this column. Then second guess for weights is this much. And what we want to do is we want to compute that how much is our overall error. Okay, so what we did was we basically computed this. Are you okay? So what we want to do is we want to subtract, and our actual was 1 and 2. So our actual is 1 and 2. Prediction for first set of weights, first guess of weights is this much, second guess is this much. So we are subtracting our actual from predicted, and therefore we are getting this. Got it? So we want to subtract 1 from here, 2 from here, not the other way, that 1, 2 is subtracted from this and then this. No, we want to, whatever first guess we are making, from that we are subtracting this. Okay? No, not clear.
Sandeep, can you repeat the multiple weights part?
Yeah. So see, what are we going to do in this exercise? We will tweak one weight at a time. Let's say, right, our weight was 1, 2. Initial guess of M and C was 1, 2. Correct? Now, we are going to make a slight increase in first wait once. So this is my first guess, and this is my second guess, right? So this is what I'm going to do. I'm going to tweak each weight at a time and then compute the error. Am I making sense? No.
Why are we making two guesses? Like earlier, we used to make one guess and tweak only that one.
Yeah. So what we are trying to do is basically, if you have, let's say, two weights, 1, 2 are two weights, right? So first time we'll try increasing this knob a little bit, just a little bit, and then we will independently tweak the second knob, okay, keeping first one as is. Whatever is the first one, we don't change it. We just don't touch the first one. Just like in differential calculus, if you have multiple variable to differentiate with, what you do is you differentiate with respect to one variable at a time. Here also we are doing the same thing. We are tweaking only one knob at a time. Okay, so if you have like 100 knobs, you will have like 100 times you will tweak one knob at a time. First, I tweak this knob, then I tweak the second knob. Okay. First, as I tweak the first knob, this is my new set of weights. When I tweak the second knob, this is my new set of weights. Then I compute y for this one, y for this one. Then what I do is from both of them, I subtract the actual value of y and then compute the loss. That in this case, the loss was this much. In this case, the loss was this much. And then I compute the rate of change of loss with respect to each W1 and W2. Got it?
So like having two guesses would make the process of predicting the error faster, predicting the y faster.
Yeah, yeah. So basically, if I just made, incremental changes to one and to both together, how would I know which variable has caused the loss better? Okay. So what I want to do is I will just tweak one weight at a time, but compute the y predicted full array in a single shot. Rather than going in a loop, I'll just ask the NumPy to do it, because NumPy can do the column, the dot product, and then get it done. So I'll basically, I should take a better example, a simpler example to walk you through this. What do you say? Okay, because visualizing the dimensions is the most important thing in this case. Okay, and I want you guys to be with me on this. Okay, and let's take a simpler example. Okay, so
Sandeep,
let's
one
say,
question. So you were saying for each weight tweak, we'll have a loss and we'll use that loss to modify the weights. So
yes,
the number of rows in the weight matrix will be the number of weights. Like if there are 4x variables, so it will be 5 rows in the weights matrix. Is that it?
come again.
So
Please.
if we have like x1, x2, x3, x4, and one constant, so we'll have 5 weights, W1, W2, W3.
X1, X2, X3, X1, X2, X3, X4. Okay.
Yeah, so we'll have 5 weights, right? W1, W2, W3,
So these are columns, right? You are saying these are columns, correct? If you have 4 columns in your data, then there will be 5 weights.
Yes. So will there be 5 rows in the weights section as well, since we are using multiple weights?
Yeah. So what I'm saying is, yeah, correct. Because what we will do is for each of the weight, we will just tweak one weight at a time. So there will be 5 set of weights.
Okay.
Got it?
Yeah. Okay.
Yeah. So I think let me just take a better example. Let's say we have 3 data points. Okay. let's say our secret equation is y equal to 3x plus 2. Okay. And for x equal to 1, okay, how much should be y? 1 plus 3, 4 plus 2, 6. Okay. So let's say 6. No.
5.
5. So we'll just say 5.1. Okay, 1 comma 5.1, right? And then for let's say x equal to 2, how much will be the y? For x equal to 2, how much is the y? 8. We'll just call it 7.9. Slightly different, okay? And just adding a random number or something. Okay. For y, x equal to 3, what will be the value of y? Or should we just leave it at 2? Let's just leave it at 2. Okay. We'll try to, no, but that doesn't make sense. It'll basically fit any value. So we'll just take one more data points. For x equal to 3, it'll be 11. So y equal to, let's say, 11.1 and x is 3. 3 comma 11.1. Okay, everybody okay with this? So let's say our data set looks like this. Okay, x is right. This is how our data set is. 1. First row is 1, 2, and 3. This is our x. Okay, everybody okay so far? And y is equal to 5.1. Okay, and then 7.9 and 11.1. Okay. All right. Right now we have this. This is our data set. This is how it looked like. Why have we put 2 dimensions in capital X? Quickly. Why have we done that? Because X usually will be multi-dimensional. There will be more dimensions in the input. So right now we have only 1 dimension, but that's about it. Okay. So our strategy is going to be, first of all, we will convert them into NumPy array. Okay. Let's say this is our data set. Okay. So, all right. So this is our data set. Now, let's say we are making a guess of, the weights. Okay. We'll use np.random, or we'll just say okay. There will be m and c, correct? There are 2 variables to this. Okay. So our w will be, let's say, 1 comma 2. Okay. That's our w. Okay. That's the initial guess. Okay. This is our initial guess. We need to find those w's that fit our data. This is our data. Okay. Everybody okay with this problem statement so far? I've just super simplified the problem, and we'll code it up and then translate and generalize it for all sizes. Okay. Right? All right. So let's say we made an initial guess for W. Okay. And that initial guess is 1 comma 2. Okay. Now our value of y predicted is equal to model capital X comma W. Okay. Is it okay? Let's just see who can help me quickly. It says 3 comma 4 comma 5. Is that right? No. The reason is that's correct, right? This is the predicted value of y. There are 3 instances and 3 predicted value. And now I am saying minus y. So this is my error, right? So this is my predicted value. Okay. And I'm saying np.sum. All right. So far, everything looks cool, correct? No? Yes? No?
Yes.
Okay. All right. Now, what we did was we took this. Okay. So this is our actual, right? This is our, okay, initial loss. Okay. Initial loss. Okay. I'm putting it into this variable. Yes. Perfect. So we made a guess for W. We predicted Y and we subtracted the predicted value of Y, then summed up the square values and we got the initial loss. Happy? Okay. Now we are saying, basically we are changing W little bit. Each of W's we are changing just tiny bit. Okay. Let's say we are increasing this by this and this by this, or I'll just call it delta equals 0.01. And I'm saying increase the first value using this and second value, sorry, should I try with some way of how would you do this like in a easier manner? Okay. Okay, who can help me with this? This is what I want to do when, okay. All right. How would we do programmatically? Anyone?
Can we use for loops?
No, you're not allowed to use for loop. Okay. Notice that we added, let's say we were given 1, 2, okay? And we added basically to 1, 2, we are adding more values, right? How do you do that?
Can you
Okay.
create
Why?
What?
can you create a identity matrix with 0.01 with delta value?
Yes. Okay. So we will call it like diagonal matrix. So let's just see if we can do this. Why are we doing this? What we'll do is we will increase. So this was our initial guess of W. Okay. And that gave us this much loss. Then we increased W a little bit. Now our new predicted value is how much? New predicted value is NP. New predicted value is how much? Model X and W underscore. Okay. So that's our new predicted value. Okay. Now using this new predicted value, these are the new predicted values, right? Now what we are going to do, we are going to subtract our Y. This is our Y. Okay. So our new losses is going to be new predicted values, okay, minus Y predicted, okay? And I'm going to say reshape, okay? And this, so that basically our actual value is how much? 5, how much was the actual value y, right? Y is how much? 5.1, 7.9, 11.1. Okay. So we are going to, subtract, what was that value? 5.1, 7.9, 5.1, 7.9, 11.1. Okay, we are going to subtract from each of them. This minus 5.1, this minus 7.9, this minus 11.1, this minus 5.1, like that. Okay, so let's see if we are able to achieve this using this. Okay, so what we did, we changed our y predicted from a single D array into such that it has one element in the last, and let's see, new error. Okay, I'll just change its name to new error. Okay.
Why it is y predicted? It should be y, right?
Oh, it should be y. Thank you. Okay, is this okay? So here, I'll just take a look at this. Okay, so this was, yes. So basically, when we took the initial assumption of W, it gave us this much of initial errors. This is errors, and then this one is giving the loss. Okay. All right. And what's that? We are call it diff, or we call it error. Okay, that's easier. Okay, so let's go back to the beginning. Y is this, Y predicted is this, Y predicted minus Y, error is this much, and this, and okay, so this much was the error for the initial values of W. Then we added little delta to all of them. Okay, and then new error is this much. Okay, now for the new error, okay, we are saying new error minus, how much was the previous error? Sorry, new error is this much, correct? Now what we are going to do, we are going to square all of the values. Okay, we are going to square all the values. Okay, so this is my, okay, this is my squared error. Are you guys with me so far? So I squared the error. Okay, I squared the error. After changing first W, after changing first W, we got this error. Then second W, I got this error. And right, this is squared error. And then I'm going to say, right, the total loss equals to NP dot sum. And what should be our dimension? Our dimension should be, the excess of summation should be 1. Okay, let's see if, am I right? Okay, so is this okay? No, excess should be 2 in this case. No, excess should be 0. Let's see. Okay, this seems to be more reasonable. Make sense, everyone? So I summed up this error, okay, this error and this error separately. Instead of summing up this and summing up this, I'm summing up column wise. Is this okay?
Why are we adding delta one by one to the like why are we adding delta one by one?
Basically,
can you scroll up?
This is this is for first set of W's. This is second set of W. When we changed M, this was the error. When we changed C, this was the error. So we totaled these values together, then these values together, and that's what we've done.
No, my question was like, can you scroll up a bit?
Okay. Where?
Yeah. Input 61.
61. This one?
Yeah. Why are we
This
adding delta? One
Okay.
like
Yeah. So what we are trying to do is let's say we got two weights. Okay. Initially, we basically chose their value to be 1, 2. Right? This is our M and this is our C. Okay. Now we want to do two things. One is first we'll try tilting M, and second we'll try tilting C. Like twisting a little bit, just increased Y, C a little bit, observe how it's changing. So there is a loss due to this, and then there's a loss due to this, there's a loss due to this, okay? Okay, but notice that we will compute the loss just by increasing only one at a time, okay? We won't do this, we won't increase both of them. Otherwise, we will not know how is error impacted because of M and C. This is our initial loss. This is our loss due to increasing M. This will lead to loss due to this. And then we will compute rate of change of loss with respect to M, which will be same as Lm minus L0 by delta, and C, Lc minus L0 by delta. Got it? So we have first set of weights where we only increased M, not C. Just a tiny bit, okay? And then we did not increase M, we only increased C, observed how much is the error, and then we computed this. Delta L by delta M is Lm L0. Not making sense still?
No, understood.
Yeah. So very simple.
I got it.
Okay. For everyone, very simple. We took an assumption of weights that gave us L0. Okay. Then we increased W, and then we got losses and so on. So what we'll do is we will design a function to compute losses. Okay. We'll design a function to compute losses if weights are given to us as an array. Okay. And once we have that, then we'll subtract the L0, and that should give us the good results. Okay. Let's see how it goes. Okay, good. Very good exercise. I hope everybody's awake. No. Okay. All right. This is going to be good exercise, everyone. Please pay attention. Help me out as well. Okay. So we calculated the losses, right? This is the new loss. This was the initial loss. Okay. So we got the initial loss. Initial loss seems to be a single number, and the loss, this seems to be a array. So we'll say loss minus initial loss, right? And that is this much. And we divide it by delta. How much was the delta? How much was the delta that we chose? This is the delta. Okay. So we calculated the rate of change here. So this is the gradient. No, this doesn't seem like nice thing. Wait. The initial loss is how much? This. And loss minus initial loss divided by delta. There is a decent amount of this. Okay, now we got the gradients. Okay, this is our gradients. Okay, okay, and bam. So these are our gradients basically, and then what we'll do, we will go to W, right? So we'll say, okay, we'll say W minus equals to eta times gradients, and eta is how much? 0.01, and bam. Okay, it says that eta times gradient. Okay, what? Isn't the W like an array? So we took the W like this, and then we are saying eta times gradient. Okay. Okay. And like this. Oh, you can't subtract it like this. Okay. All right. Okay, I'll just again go up because I messed up with the W. Okay. Now my new value of W is going to be how much? Okay. All right. So it increased the W by a little bit and so on. Okay. And we can keep on repeating this process. Okay. Is everybody okay with this? What I've done just now? So this is a single epoch. Okay. This is the data that is given to us. We made an initial guess for W. Okay. And then we tweak this. Okay. So this goes in a loop. This is from here, the iteration would start. Okay. For given W and X, it'll predict Y, subtract each value of Y from the predicted value, and then it will compute the error. So this is the initial error. Okay. And we'll basically keep it like this. And okay. So let's do this again. Now this time I'm going to refactor this code into two parts. First one is going to be something that computes the loss. Okay, so it'll compute the losses given the weights. Okay, so let's define the function for loss. Okay, given X, W, Y, and W. What it does is it basically uses the model. Okay. I don't like this idea of keeping to add once every time. Okay. Should we do this? Right. Okay. We'll do that again. We'll do the optimization again. Right. So yeah, we'll do that optimization again. So first of all, what we did was we are defining a function called loss. Okay. Let me copy paste the code. Okay, how did we compute the loss? First of all, whatever weights are given to us. Okay, weights is an array. We call the predicted value like this. Okay, predicted value like this. Okay, there we go. Perfect. Now we come down here. Okay, so this is our new error. We'll just call it error. Okay, we'll just call it error. Where is my error? Yeah. Okay, so you can see error. So we predicted the value here, subtracted the predicted value with y. This is my error. Now what I did, I calculated the squared error. Okay, squared error. Okay, and then I did the sum. Cool. I did the summation. Okay, and return the loss. Happy? And I'll just call it loss function. Okay, so shall I test it again with this whole process? This was my capital X, this was my W, and yeah, then I did here. Okay, this is my initial guess of W. Okay, initial guess of W. And this was my predicted value and this. So let's see if I can use my loss function like this. Okay, what was the name of my loss function? LOSSF. And I'm giving X and I'm giving Y and W. Okay, so it is not working well. Not working well. Let's see, where did I make mistake? Okay, so this is my X. This is my W. Okay, this is my predicted value. Okay. All right, it is not giving good results. Anybody, any idea? So this is my loss function. I'll tell you why. Okay, here, this is my loss function. Okay. It does is, it basically calls, oh, this is the mistake. Okay. Again, it's not doing a good job for me.
The error in loss function should have predicted instead of new predicted.
So line number 3 and line number 4.
Okay. It should be like this.
And even on 4, it should be new error or just an error?
You are right. Oh man. Let's see. Okay. Now, here is a mistake that is happening. Why? Because the W that I'm passing is a single dimension array, right? So what I need to do is, when I'm creating this initial guess, what I got to do is I got to put it like this. Okay. This is going to be my weight like this. Okay. And all right, what happened now? Okay, this is my X, this is my W. The Y predicted minus Y. Okay, and okay. Now, yes, this Y also need to be reshaped into the same format. Okay. This Y need to be reshaped into the same format as we have done before. Okay, I'm saying reshape and okay. Now it makes sense to you, right? So Y, so X is M times number of M times N. Y is M times 1. Okay, so I have reshaped it such that this reshape means that if, let's say, this reshape means, as I discussed earlier, let's say you have 2, 3. This means convert this array, convert this array into 2D array such that the second dimension has got 1 value and rest of the elements would be as is. Okay, so it'll convert it into this. Okay, so reshape basically reshapes an array into different sizes. What it does is it puts all the elements as a sequence. Then based on the number of columns and rows that you have specified in reshape, it will rearrange. One of the values in reshape, you can leave it leave it as -1, it will automatically calculate how many values are supposed to be there. Okay, so here we are saying translate this into something cross 1. That's what we are saying. Translate this into something called cross 1. And how many elements will be there? So it'll translate it into this. We could as well write it like this. We could also say, translate this vector into an array of 3 rows and 1 column. Everybody okay with this? No, yes, no, no.
But why are we doing this?
Because when we are subtracting, right, when we are subtracting values, we want it to be subtracted in a way that predicted y, okay, should be subtracted from corresponding value. Okay, that's all we want to do. Okay, because y, yeah.
In the loss function also we are doing this reshape, right?
Yeah. We should avoid doing this here. When we are passing y to it, we will reshape it outside.
Okay.
Okay. So basically, the challenge is that if you, in case of NumPy, right, let's say you have 1, 2, 3, okay, and you are subtracting, okay, you are subtracting, say, 5 from it. How should I do? So basically, if you look at it here, what's actually happening is that if you do not do the reshape, okay, if you do not do the reshape, what happens is that it ends up computing this error like this. So it subtracted the y. This is the actual y, and so on. So for each one, it basically just broadcasted these variables, right? 1, 2. Yeah, if you look at it here, I think you'll get a picture. So this is our okay. Yeah. So our predicted value for the model is 3, 4, 5. Okay. The y predicted has got this shape. Okay. From this shape, if we subtract 5.1, 7.9, 11.1, what's happening is it's getting converted to like this. Okay. So 5.1. So 3 minus 5.1, 3 minus 7.9, 3 minus 11.1, and then again 4 minus 5.1, 4 minus 7.9. Just because there are two different dimensions, it's kind of messing it up. So it's better that we basically reshape our y into this, okay? Into this. That will fix it. Okay. So predicted y is 2D array, and we want to do the same thing for right here. Okay. So I think we don't need this anymore as long as we have already reshaped it. Okay. So expected value is x should be m cross n, and y should be m times 1. Okay, and w has to be n plus 1 times any numbers. Okay, any w's. So for each right, if you basically are going to use the w to be anything, usually this is how it's going to be when we are computing gradients. This may or may not be the case. Okay, so how should I write? I'll just put it -1. -1 means w could be anything. W could have any number of rows. Okay, we will pass hundreds of sets of w's or two sets of W's or one set of W, and we'll get the good results. Okay, W must be having, no, this is wrong. Okay, W will be any number of rows, okay, any number of rows times n plus 1. N is number of features, one more than that. Okay, all right. Everybody okay with this thing that we're doing here? Good. So we calculated the loss for this one, initial loss. Okay. All right. All right. Now, so this is our initial guess, and using this, we calculated this, right? Loss. Happy? Now, the same philosophy we are going to do here. Now, first important thing that we did last time, yesterday, or in the previous class, what we did was we found the new W's, right? So first we filled it with zeros. Okay, we filled it with zeros, and then, okay, then add a W to it. Okay, so we need to do this here. So we calculated this. Okay, now this part which we did manually, can we do it here? Okay, we are saying, okay, define, okay, increment W, okay, given whatever W we have, right, whatever W's we have, it is going to generate, the np.zeros, and what was that thing? Is going to take W, whatever W we have, and increase each one, increase each of them. Okay, so how does the W look like here? Okay, so we'll take the W dot shape. Okay, we'll say W dot shape. Okay, and W dot shape is this, shape minus 1. Okay, it would give us the second, right, number of W's. We are filling this matrix with number of W's like this, and then adding the delta to it. Okay, we are adding delta to it, and we are also passing delta here, and we basically, okay, so what we are doing, okay,
We are creating a zero matrix and we are adding diagonally, we are adding that delta to each one, and then we are adding the W matrix to it. Right?
yes, yes. Okay, this is a wonderful exercise what we're doing right now. Okay, yes, let's see what is happening here. It is saying for none type, it is not allowing us to do anything. Okay, let's see. Okay, so print W dot shape. Okay, and print num W. Okay, so it is 2. So then we produced A. Let's see how it looks. A. Okay. A looks like this. Okay. And then we are saying fill diagonal. Okay. Let's call it diagonal matrix. Okay. Print diagonal. Okay. So it says, we are not supposed to be doing this. Yeah. makes sense. Okay, it's essentially what it is doing is it is just putting it here. Okay, so right, I think I'll just show you how it looks like. Print A. So here, first, right? First, we calculated the shape of W. The W basically is 2D array 1, 2. This is the shape. Okay. This is the not shape. This is actually the value of W is how much? Let's see. Yeah, the W shape is also 1, 2. Values are also 1, 2. Okay, don't get confused. Okay, so what we are trying to do is from 1, 2, we want to produce this data. Okay, first we increase this, second increase this. So what we did, we first generated 2 by 2 array filled with zeros. We first generated 2 by 2 filled with zeros. Then we filled the diagonal with the delta. Okay, and then once we do that, then we add this to 1, 2, and it becomes, that's it. Yes. So basically, rather than hard coding, we basically did this. Make sense? Happy everyone? Okay, there we have it. Perfect. Yes? Okay, now we can again call the same loss function on the W dash, right? Let's see how does the loss look like with the W dash. Okay, so we'll say loss capital X, Y, W underscore. Good. So we are all good. Make sense, everyone? Cool, right? Simple. So this is my, okay, now this is our predicted value, right? This is our previous loss. Okay. I'm deleting this one because we have another loss function. Okay. We have, this is our previous loss. Okay. Previous loss. And right, this is our previous loss. Now what we do is we basically call this function for new W's. Okay, good. And then we compute the new loss. Okay, how did we compute the new loss? This way. Okay, all right, this one. Okay, we'll call it loss equals to this much. Okay, now let's just go slowly, one step at a time. So this one gave us the new loss, correct? This is a new loss equals this, and am I making a mistake anywhere? Okay, new loss is this, happy. Now let's just see if gradients are computed properly. Okay, and right, so new underscore loss, okay, is this minus the initial loss is this much, okay, and that's it. Perfect. Am I making sense? Okay. All right. So that's about it. We will do this here. Okay. And yeah, should I pass this delta also in this increment W? Okay. And this will give us the gradients. And then once we have computed the gradients, okay, once we have computed the gradients, then we can simply say this. Okay. All right.
Why are we passing delta twice in the increment W?
Where?
In the increment W, we are passing the delta twice there.
Increment W. Oh, we are passing delta twice. Yeah, it was unnecessary. Thank you. Because we anyway are, yeah, we were using it already. Okay. So notice it that basically this is a compute gradient part, and this one is update gradient part, right? So we will use the right. We will say we'll separate out this two logic. Okay, we'll say define. Okay, define. Right. What do you call it? Model underscore fit. It takes x, y, and number of epochs, right? So what we're going to do first, we are going to, okay, this I'm going to just comment it out for now. Okay, so these are the gradients that it computes and returns. Okay, so it basically, right? So what we do is we take W, okay, and yeah. So model.fit takes x and y. Okay. First of all, we'll do a y equals to y dot reshape. Okay. Y dot reshape to whatever it is. Right. That's one thing that is pending on us. Okay. And what else we had to do? We need to clean up everything. Okay. Interesting. Interesting. Okay. It's good that we are doing this exercise because doing it with the loops is a one thing, and doing it here is another. Okay. All right. So I've just cleaned it up. Okay. So perfect. So we have the loss function, which takes x, y, w, and then we have here we have the model function. This is the model function that we have written above. Where is the model function? We copied it, right? Yeah, here. Okay. Now my stuff looks a little more neater. Perfect. So we have a model. It takes X and W, and then it produces Y. Okay. And then it basically computes the loss. It calls the model in X and W, and then it predicts Y. And please note that here we should make sure that okay, this one will actually give us the value of W's. So we have to make sure that these are the correct dimensions. Okay, so the correct dimensions, X is M cross N, Y is M cross 1, W is any number of rows times N plus 1. Okay, that's what we have to do. And this one, oh, this one actually just adds one more dimension. So we just have to not pass this. Okay. So yeah, this model will add ones to it and then do the thing. Okay. We can further reduce it. Okay, we'll reduce this overhead later. Okay, and we define the loss function. It calls the y, gives the predicted value, then it computes the error, then it squares it, and then it sums it and gives the losses. Okay, if there are many rows in W, it will give many losses. If there is only one value, it will give one loss. So how many ever set rows are there in W, that many losses it would return. Okay, then it would compute the gradient. How does it compute the gradient? It will basically compute the previous loss, increment W's, then compute the new loss. Okay, and we call it new loss. Okay, and new loss minus initial loss divided by delta. There could be multiple new losses if there are multiple rows in W. If there are multiple sets of W's, it will produce new losses, not loss. And then we get the gradients, it returns the gradient. If there is one, how many gradients will be there? If there is one row in W, it will return one gradient. If there are 10 W's, then it will, sorry, the number of n, how many columns are there in W, that many ones. Okay, and then basically this anyway is where is this used? This is used here, so I'll just put it above this to ensure that we are on the same page. Perfect. So this is our model, this is our loss function, this is our increment, and then this is our right, single epoch. Okay, so okay, single epoch. So we'll just call it okay. Okay. Okay, it just right, model.fit. What should I name this function? I want to call keep a function that basically takes W, okay, and gives new weights. Okay, it takes X, it takes Y, it takes the epochs. Okay, how many? Sorry, epochs we can ignore for now. Single epoch. Okay, single epoch. It takes the previous value of W. It returns the new values of W. Okay, and yeah, I'll just assume that this is like this. Okay, so that's it. Yes, so what it does is it basically applies the gradients here. Okay, so let's say it would compute. Okay, so it will compute the gradients. It would compute the gradients using X, Y, and W. Okay, these are our gradients. Okay, multiply them with eta. Eta is a learning rate that is here, and that's about it. Okay, will it work or will it just burst? Okay, let's see. Okay, so I'm actually anxious. Okay, so if 1, 2 was my W, okay, how much was my initial values of X and Y? Yes, okay. Will it work?
So in 157, you need to change the grad equals to new loss minus previous loss. Right now it is written initial loss.
Oh yeah, thank you. Yes, okay, perfect. All right, let's see. Okay, so it says new weights X, Y, and it says initial loss, predicted value. List object does not have any of this. So we have to say np.array. Okay. Not bad. 1.56, 2.24, 1.56, 2.247. Okay. Is it making sense? If I restart the kernel, okay, I'm restarting the kernel, okay, and will it still work if I just do NumPy, okay, go down from here, done. Yes, it works. Okay. All right. So so this is our step, single step. Okay. There are multiple names for this. People use this in many ways. So what we can do is we can print here. We can print, say, loss at every stage, compute gradient, new loss. Okay. And okay, so we can essentially just print the loss. Okay, that probably gives us print. Okay, or we can also just after at every stage we can keep on printing the loss for okay. Just before we start, we can also say loss x, y, w, okay? And we can also say here, okay? Now we are saying w equals new weights, okay? And then again here, okay, I'll do this way. Okay, so I'm going to say for epoch, for I in range 10, okay? Make sense? Yeah, everyone? Okay. All right, so it kind of figured out 2.68 plus 2.68. Is that wrong? Mm-hmm. Okay. I think we can forgive it here, right? So it kind of reached 3x plus 2, right? Y equals to 3x plus 2 is what we had started with. So it is able to figure that out. You can see that, right? Everyone? So it's basically, yes. So this is kind of able to figure it out, right? For this data. This is our simpler example that we took, and it is able to solve this. Make sense? Okay. Hello, everyone.
Yes, Sandeep,
Yes, sir.
I thought we should not be using this for loop.
This one.
Uh,
No, this is okay. This is okay. Basically, the reason we are doing it is here we can't avoid it because it's a very important question that you have asked. That why are we using for loop? Can't we do something else? The problem is the weights computed in previous steps are being used in the next step. So this will be sequential operation. You can't really make it parallel in any way. Okay. So, right? Even if you have like 20 computers, you can't use that because to compute the next step, you need the previous one. Okay. So usually there is a slight variant of this one where you let the two computers compute the weights, like first computer and second computer, and then take the average weight of all of them and update the W and then distribute it back. Okay. So to compute the next weight, you need the previous weight, and therefore you can't really parallelize it. And therefore, you can't really use any of the map function or matrix function and so on. Okay. So that's a very important question. Everybody okay? No? Yes.
Yes, sir.
Yes, sir.
All right. All right. So you guys will be able to code it. It took me a long time to do it in NumPy. Oh man. Okay. But the good part is that most of it is it's pretty performant. It's going to be extremely fast. And you can just, instead of NumPy, you can use the similar constructs provided by NVIDIA's libraries. There is a Intel's libraries and so on. And there's a NumPy's local version of there, which is much more faster. And internally, what it'll do is, internally, when we do the matrix multiplication, if you see where is the matrix multiplication happening, let's see. Okay, this is where the matrix multiplication happening, correct? And right, so the loss function is calling model once, okay, and the gradient function calls the matrix multiplication once, and then once again here, okay, as many weights you have. So if you have, let's say, n columns, it's going to call the matrix multiplication n times, right? That way, and then you have. So the complexity of gradients is something that you should pay attention to. Okay, it's essentially just we broke down everything into matrix multiplications, and the GPUs have made these matrix multiplications really fast, and therefore this code will be able to take the advantage of the GPUs. Okay, so there we have it. Let me just commit this code, and yeah, any questions before we call it a day? It's very important. I think this is the right way to learn NumPy. We are basically coding it up, and probably the most involving example and most practical and real example is gradient descent out of all. Okay. Okay. Any other question before we hang up? No? I'll put you to sleep. You're on mute. I think you are scolding a kid.
yeah, I was talking here.
Okay. All right. So yeah, any questions, Nikita, Aman, Ayush, Ayushi, Lakshesh?
No, Sandeep, I'm good.
No, sir.
Yeah. So see, the thing that we did today is how people usually do things. Okay. You basically take up a small piece at a time, and you are not expected to know everything, right? And when you are on a project, it's completely okay to keep on trying out with a small example, keep on working throughout, keep on observing. So the one thing you must have observed it, that even for me, dimensions are hard. Okay, even for me, dimensions are hard, and you kind of get lost. And that's the same scenario with even the authors of the Chat GPT. If you take a look at the code of GPT, you will be able to understand it now. I can guarantee that. Okay. So after today's session, you can just take a look at straight away, take a look at the code of GPT, the Chat GPT, the GPT-4, the one that they have made public. You'll be able to make sense of each and every line. Okay. And that'll make more sense. Like, for example, like, why did we use the diagonal matrix? Why did we fill the diagonal? Why did we do these? Those ideas are pretty simple for you now, because essentially essentially underneath, that's what is going on. Okay. And yeah, you will appreciate the fact that the one that we did, like matrix simplification, and observed each and every dimension, and why we transposed, why we did reshape. Okay. And reshape is all of these parts in the individual part that we discussed today are good interview questions. Like, for example, if you have to introduce one more column, what would you do? Why is the broadcasting happening? Like, we saw the broadcasting happening because that column got replicated twice, right? How do we do the summation? Okay, so break down each piece of code with the small examples, and then you will be able to understand each and every line. Okay, so in NumPy, what you basically need to understand is, number one, how do we do the standard operations like dot product, and what do they mean? Number two, how does the broadcasting happen, right? We have discussed broadcasting in the class, okay? But real example was today. Now, third thing is, how do you reshape the arrays? How do you change their sizes? How do you generate and create arrays? So those are the few things you got to do. Okay, so we have touched upon each and every part of NumPy. I would want everybody to take a look at it and take a look at each piece that we have discussed, and then we'll take it from there. Okay, so we'll continue from here tomorrow at the same time. And in the meantime, I would request everybody to take a look at the whole notebook, try coding your own version, try struggle with the dimensions. That's how you will get the thought clarity. Okay, struggle with the dimensions. It's okay to make mistake. Just if things don't work out, do the way I did. Break down the big piece into small parts, take small examples, and do that. All right. And yeah, wonderful. I hope this is good. This is good for you. This is the first time I'm doing it this way. Usually I go with a standard classroom way that NumPy has 4 functions and this and that. But I have taken a digression. The reason is that this is the approach that will make you feel NumPy. Okay. And not the other way. All right. Anyway, have a good day. And I want more questions from everybody in tomorrow's class. Okay. And you guys will have questions only if you struggle with it. It's okay. Even if you have not attended any class so far. Okay. And the questions you're getting, even they could be basic from your perspective. Just ask those questions. Okay. Just ask, like, I'm not clear about this. Explain to me this again. It's okay. It's completely okay. And yeah, that will benefit everybody. So don't be in that mindset that, oh, just because I missed a couple of classes in last, I am not, I'm not entitled to ask any questions. Okay. Don't think that way. So I look forward to see you tomorrow. Have a good day.
Thank you, sir.